introduce we're starting our second session now, and our next speaker is Professor Neri Merhav from the Technion, and he'll be talking about physics of the Shannon limits.
Thanks very much. First, I'd like to thank Meir and Mark for inviting me to give a talk in this meeting. The subject of my talk is about connections between information theory and physics, in particular statistical physics. And what I'd like to explore is the question of, in particular, the relations between the laws of physics and the fundamental limits of information theory, or the Shannon limits. So the idea is that while the laws of physics draw the boundaries between the possible and the impossible in nature, the coding theorems of information theory, and particularly the converse theorems, draw the boundaries between the possible and the impossible in data communication and data processing in general. So the question is there any relationship between the two things? And it has been known for a very long time, actually from the late 50s by the works of James, that there are quite close relations between the two fields, most prominently the notion of entropy, which appears in both of them. But it goes much beyond that. So the structure of the talk would be, first of all, to give a very, very brief background, the necessary background in physics, which I'm going to need, and then discuss physical interpretations of the Shannon limits that we all know, like capacity, entropy, ray distortion function, and so on. And then we're going, having adopted the point of view of physicists, look at the somewhat broader picture that is known as Dzerzhinsky's equality, which I'll present, and then see how it sheds light back into information theory, and we end up with some generalized form of the very, very basic inequality of information theory, which is called the information inequality. So I guess that all of us know what the fundamental limits of information theory are. In the very basic paradigms we have in the lossless compression, it's the entropy. In the case of ray distortion, lossy compression, it's the ray distortion function. In channel coding, the channel capacity. The first talk was about polar codes. This was one class of codes. In the combination of source coding and channel coding, which is joint source channel coding, we have a certain limitation of the end-to-end distortion between the source and the destination, which is given by the distortion rate function computed at capacity, which is the inverse to the rate distortion function, and so on. Of course, one can go to more complicated situations where you have side information, multi-user situation, and so on. But the point is that I think that all the fundamental limits of information theory, or virtually all of them, which are given by the converse theorems, are based on some way or the other, whether it's called the data processing theorem or Fanot's inequality, or the fact that conditioning reduces entropy. These are all forms of the very basic inequality of information theory, which is called the information inequality, telling us that the divergence, or the Kullback-Leibler distance between two distributions P and Q, which are defined this way, can never be negative. This is what it's called in Cover's book, Information Inequality, and that's going to be the pivoting inequality in our talk. An equivalent form is also known as the log sum inequality, which is written here. If you have general sequences of positive numbers, not necessarily the probability distribution, AI and BI, then this summation, which looks very much like the divergence, but not necessarily normalized, is always bigger than capital A log capital A over B, where capital A and capital B are the sums. It's easy to show that these two inequalities are actually the very same. They are equivalent. And yet another name for the same inequality, which is often used by physicists, is the Gibbs inequality, and it's used in the context of probability distributions corresponding to equilibrium. So a few very basic terms in physics that we are going to use are, I'll give in the next few slides. Statistical physics is about the physics of very large systems of many, many particles or elementary units that we want to investigate how they behave collectively. And the system is actually defined by the so-called microstate or microscopic state, which is some vector with x1 of xn. Every xi corresponds to one of the particles or one of the elementary units. And with each such microstate, there is a certain energy, script E of x, and this function is called the Hamiltonian. So a very simple example, if every xi is itself a vector which is composed of the momentum and the position of this particle in space, then a very classical example of a Hamiltonian is composed of the kinetic energy and the potential energy of each particle. So that's a very simple example. Now, one of the basic results in statistical physics tells us that when we have a system with such a large number of particles and it lies in terminal equilibrium with its environment, then the probability distribution of the various microstates obeys the so-called Boltzmann-Gibbs distribution, which is given by an exponential function of the Hamiltonian with a coefficient in the exponent, which we denote by beta, and beta is the so-called inverse temperature. It's 1 over K times T, where K is Boltzmann constant and T is temperature. And a very important role is played by this normalization constant and the denominator, which is also called the partition function. Its role is much deeper than just being a normalization constant. Actually, all the equilibrium physics can be derived from this function. For an example, the free energy, the internal energy of the system, and the entropy, and the heat capacity, and many, many others. Now, from these definitions that we just saw in the previous slide, one can easily identify the relation, which is also known in thermodynamics, telling us that the free energy of the system is related to the energy and the entropy by this equation. And the physical meaning of the free energy, or more accurately, should I say, the difference between two free energies, is that it is the minimum amount of work that one has to apply to the system in order to pass it from one equilibrium state to another. And this at fixed temperature. And this minimum is achieved when this transition is done slowly in a reversible process. Namely, that it is slow enough that the system remains almost all the time in thermal equilibrium. In every other case, the amount of work that we have to apply is larger than the difference between the free energies. Now, let us take two possible Hamiltonians of a given system, E0 and E1, and say fix the parameter beta of the temperature, and consider the Boltzmann distributions associated with both. Then, if we apply the information inequality, namely the non-negativity of the divergence between the two distributions, then it's easy to do because of the exponential form, which cancels the logarithmic function, and we end up with a very simple inequality telling us that the expectation of the difference between the two Hamiltonians taken under the probability measure P0, namely take here I equals 0, is never smaller than the difference between the free energies, which we, as we said, that's the minimum amount of work that has to be done in order to pass from one equilibrium state to the other. So here's a very simple physical interpretation to this inequality, which is nothing that other than the positivity of the divergence. Suppose we have a system in equilibrium which is initially with Hamiltonian E0 for all negative times, and so its free energy is given by the negative logarithm of a partition function corresponding to E0. At t equals 0, the Hamiltonian jumps abruptly from E0 to E1, namely we inject all of a sudden an amount of energy which is given by the difference between the two. And this can be done by applying an external force or a field, say a magnetic field or an electric field, depending on the system. And then after this abrupt energy injection, we let the system relax again, and it equilibrates at the new Hamiltonian E1, and so its free energy is given by the negative logarithm of Z1. So we have a system in equilibrium at E0. We then give it a bang at time t equals 0, and then let the system relax at the new state. So what we have shown is actually the interpretation of the positivity of the divergence actually tells us that the amount of energy that we injected can never be smaller than the difference between the free energies, or in other words, more accurately, the difference between the two. I'm not getting along with this. The difference between the two is exactly k times t times the divergence between the two measures. And so this difference is actually the amount of energy that is wasted, that is dissipated. And this dissipation is in the form of, find its expression in entropy production, namely the entropy of both the system and its environment might increase. And this is because we applied the force in an abrupt way, in a sudden way, rather than using a reversible slow process. So that's the physical interpretation of the very basic, very most elementary inequality of information theory, which stands behind, I think, every converse result in information theory. Let us look at a few examples. The first example is of a Markov process, a binary Markov process taking values in -1 + 1, which I chose this alphabet deliberately because it gives us the idea of spins with two different polarities. And we have, the data comes from a Markov process P0 with given transition probabilities, given by this form. Whenever the Markov process has symmetric transition probabilities, we can always represent it this way. in the binary case. And but suppose we want to compress the source losslessly, but the co-designer has the wrong idea about the true information source that generated X. It thinks that X was generated by another Markov source with asymmetric transition probabilities. We have here another term. The J is the same J as before, but we have some offset. So the divergence between the true distribution and the assumed distribution has the meaning of rate loss in lossless compression, the redundancy that we're going to pay for using the wrong probability distribution. Now it is easy to see that if we look at these two probability measures and we take the product over all times, we can identify the corresponding Hamiltonian of the Boltzmann-Gibbs distribution, namely E naught, which is J times the summation over all times of products of consecutive X's, which is just like the interaction energy of spins in the Ising model of magnetic materials. Whereas for the second measure, we have another Hamiltonian where the first term is the same as before, but we have an additional term with some parameter B, which is related to the original parameters J and K, which acts on the sum. Namely, it has the interpretation of a magnetic field acting on each one of the spins of the system. So the difference between the two, W, the amount of work that we do on the system, is exactly the one associated with applying a magnetic field on a bunch of spins. So here redundancy has the physical meaning of magnetic work, actually, that is done by a field. Another example, similar one, but now instead of the Ising model where the interactions between spins are only between neighbors, here we take P naught to be the same as before, but now we allow interaction between every two different spins, not necessarily only neighbors. Then we can, by analyzing the divergence here using methods of statistical mechanics, one can arrive at an expression of the redundancy, namely the divergence between the two measures, as something that is associated with some optimization problem. And it turns out that this maximizing parameter theta is discontinuous in the parameters of the problem, B and J. So, for example, if the magnetic field is 0, and J, if J is large enough, namely the coupling is strong enough, and we let B vary from negative values to positive values, we have all of a sudden a jump in the maximizing theta. And this causes a discontinuity of the derivative, and we get actually a phase transition in the term of the redundancy. Namely, the method of statistical physics can teach us something about the behavior of redundancy in some models of source coding. The third example in this context corresponds to hidden Markov models. Here we have two distributions. One is we have a pair xi, yi. Under one distribution, it is IID. Under the second distribution, we have a Markov source and a memoryless channel. And if we look at the output marginals, namely the marginals of y, so in the first case, it's still IID. But in the second case, when we sum over the Markov state, we're actually getting a hidden Markov process. So now, if we look at the information inequality, which is, as we said, equivalent to the log sum inequality, we can use it in order to get a lower bound on the probability of the hidden Markov model. And this bound is computable rather easily because these two guys are products, and the logarithm acting on the product gives us sum of terms that can be handled very easily. And after optimizing this lower bound, maximizing it with respect to P naught, we can get a bound on the entropy of the hidden Markov process. This is an idea that is actually used by physicists quite a lot in order to get bounds and free energies of complicated systems. I'm not going to delve into this any further, but that's one possible idea. So now if we get back to the data processing theorem, the data processing theorem tells us that if we have a Markov chain, XUV, then the difference between the mutual informations, which can be seen as the expectation of a certain divergence between two probability distributions, can never be negative. And so one of the instances of our interpretation of the information inequality, it can actually be attributed to the data processing theorem. So we can think of two Hamiltonians. One is the negative logarithm of the probability of x given u. The other is the negative logarithm of the probability of x given v under this Markov structure. The partition function, which is just the sum of probabilities, is exactly 1 under both measures, just the sums of two different distributions. And so the two free energies, which are the logarithms of these guys, are both 0, namely the change in the free energy is also 0. So now if we compute the average work injected by this abrupt change from E0 to E1, then we get exactly the difference between the conditional entropies, which is also the difference between the mutual informations. And so we end up with the inequality, which tells us that the difference between the two mutual informations is actually, can be thought of the average amount of work that we apply to the system under this setting, while the 0 in the other side is actually the change in the free energy. But since the free energy doesn't change, it is 0. Let us look at a few more examples in this context of the data processing theorem. And that's the simple example of the degraded broadcast channel, the Gaussian degraded broadcast channel. Again, we have a triplet, a Gaussian triplet, which is Markov VUX. And suppose that they are formed as a cascade of two channels, one with noise N1, with variance 1 over beta 0, and one with noise N2, where the two noises together have, of course, a higher variance. Now, if we look at the difference between the two mutual informations, these are the difference between the differential entropies, this, of course, can be easily represented in the integral form, but it is actually very similar to a known relationship in physics, the relation between the change in entropy and the heat that enters into the system. And so what we identify here is actually the heat capacity, which in this case is exactly 1/2. And this agrees with the known results about the heat capacity of the ideal gas, which has no interaction. It has a quadratic Hamiltonian. So that's a rather easy example. The more interesting example is the one where we took take a look at the other difference, IUV minus IXV, before it was IUX minus IVX. And here it's about the difference between the mutual information between the clean signal and two noisy versions of this clean signal. It is known from a result by Gauche, Shammai, and Verdu that there is a relationship between, in the case of the Gaussian channel, between the mutual information and the mean squared error of estimating the input to the channel based on the output. Actually, the MMSE is half the derivative of the mutual information, or equivalently, the difference between mutual information is the integral of the MMSE. And so if we represent it in the form of a heat integral over temperature, we actually identify the heat capacity with the MMSE of the Gaussian channel. Now, why is this interesting? Because in many cases, there are effects of threshold effects in estimation, turns out to correspond to phase transitions in physics. For example, if there could be a situation where the MMSE behaves discontinuously as a function of the SNR, and so this means that the heat capacity is also discontinuous. So there is a close relationship between phase transitions in physics and threshold effects in estimation. Here's let us particularize this example even more. Suppose that the clean signal that is transmitted over this cascade of channels is actually a code word. It is taken from a finite set of vectors, m vectors, where each one of them, the number of vectors is e to the nr, where r is the coding rate. Each one of these code vectors is randomly selected from the surface of a sphere whose radius corresponds to the allowed capacity, which is p. So it turns out that the mutual information between the code word and its noisy version, with variance which is proportional to k times the temperature, has two kinds of behavior. If the rate of the code is smaller than the capacity of the corresponding channel, then the mutual information is essentially about the rate. But if it is above, then the mutual information is stuck at this capacity and doesn't grow any further. So if we take the derivative of this guy, namely compute the MMSE from the mutual information, then this non-smoothness translates to a discontinuity in the derivative, and we get that the MMSE is essentially zero as long as the rate is smaller than capacity. We can decode the code word reliably, but it becomes positive and in a discontinuous manner once the rate exceeds capacity, and it behaves exactly as if the input of the channel was an IID Gaussian process rather than a code word. So we have a phase transition or a threshold effect at the temperature or the rate at which the capacity agrees with the rate. A few words of discussion. Actually, this relationship was known by physicists before, but in a completely different context and under a great variety of limiting conditions. But here our discussions is very general. Actually, there's no conditions, virtually no conditions at all. Here we apply it in particular to the data processing theorem. What is also characterizing our setting is that since we said that the change in the free energy is void, this means that all the work that we apply abruptly is dissipated, is wasted. Nothing goes on increasing the free energy. And it also goes solely to the system under discussion and not to its environment. Now to the broader picture. We talked about the situation where the Hamiltonian changes abruptly from E0 to E1. Now let's look at a more general situation. We have a continuum of Hamiltonians with a parameter lambda, which can change between 0 and 1, so we can move continuously from E0 to E1. You can think of this lambda as some sort of a generalized force. There's a known result by a physicist named Dzerzhinsky from 1997 that tells us that no matter what is the protocol of changing this parameter lambda from 0 at negative times to 1 after some time tau, the injected energy, which is defined here, and which is a random variable because of the randomness of the microstate of the system, always satisfied an interesting equality telling us that the characteristic function is given by the negative exponent of the free energy, no matter what the protocol is. And so if we apply Jensen's inequality to this guy, we can easily see that it is never smaller than e to the minus beta, the expected energy, and so the expected energy cannot be smaller than the difference between the free energies. This is now more general than before. Before we talked only about one particular protocol where lambda is actually a step function. It goes from 0 to 1 abruptly. Here we talk about the general protocol, and it continues to be true. The case of a reversible process is the case where W is actually in the limit deterministic, and then Jensen's inequality is actually an equality, namely there is an equality also here. Now, if we look now at the broader picture, we have two different Hamiltonians given by the negative probabilities of P0 and P1, say the temperature is 1, and think of a sequence of lambda starting from 0 and ending at 1, not necessarily monotonic, it can be any pattern. Then we can look at the work done, the overall work, the difference between Hamiltonians times the differences in the lambdas, where each xi is governed by a probabilities distribution corresponding to this E lambda that we defined before, namely it's a weighted, proportional to the weighted geometric mean between P0 and P1. So we pass from P0 to P1 in a geometric curve. Then we can show something very similar to the Dzerzhinsky equality. The temperature is 1, and since the change in the free energy, as we said, is 0, we get immediately the same result as before. But if we apply Jensen on the left-hand side, we get a new inequality, which at least I am not aware of. I've never seen it before. It's an extension of the information inequality. You can think of this, of the left-hand side, as a generalized notion of divergence. And no matter what the protocol is, it is never negative. And one interpretation for this inequality has to do with hypothesis testing, because in hypothesis testing between two measures, P0 and P1, we see these guys. We see these exponential combinations between the two measures. So it gives us some relation between the two exponents of hypothesis testing. So let me summarize. I think it's about time. We have seen that there are relationships between the fundamental limits of information theory, which are all stemming from the information inequality, and the laws of physics, in particular the second law. An optimum communication system is actually analogous to a reversible process, and a suboptimum communication system is analogous to an irreversible process. Any loss in information in the system can be attributed in the physics world to wasted energy, dissipated energy, which causes a raise in the entropy of the system and the environment. And we also saw that if we look at the broader physical picture given by the Dzerzhinsky equality, then the benefit that we get is a new inequality in information theory, which is about the positivity of something that generalizes the notion of divergence, and to the best of my knowledge is new, and it has some meaning, at least in the context of binary hypothesis testing. So that's more or less what I have to tell.